Welcome to the AI Checkpoints. Before we dive in, just a quick disclaimer. This content is generated by AI. Okay, today we've got a really fascinating deep dive for you. We're exploring some groundbreaking updates in the Transformers library. These are heavily driven by OpenAI's new GPT-OSS series of models.
That's right. And if you're looking for a shortcut to understanding the latest in AI efficiency and how to scale these things, you're definitely in the right place.
Yeah, we're going to unpack how these innovations make it just incredibly efficient to load, run, and even fine-tune these, large language models.
And what's really fascinating, I think, is how these developments in transformers aren't just for GPT-OSS. They're bringing in some really novel techniques, things like MXFP4, quantization, efficient kernels, advanced parallelism. These are things that are set to benefit a whole range of models, both current and, future ones.
Which raises a big question, right? How do these super technical upgrades actually translate into, real improvements for someone working with AI or even just curious about it?
Exactly. We'll try and connect those dots for you today, drawing on some great insights, particularly from an article digging into the tricks from OpenAI's GPT-OSS release.
Okay, let's unpack this. Maybe start with one of the foundational bits, zero-build kernels. Now, we know kernels are these specialized programs they run on accelerators for heavy lifting, like matrix math. But transformers traditionally had this challenge, right, with custom kernels causing dependency bloat and needing compilation on your machine.
Oh, absolutely. That was a huge headache because, as the source material points out, these custom kernels, often, low-level CED code mixed with C++, they had to be compiled locally on your system. You can imagine the pain trying to build systems right across different setups.
Yeah, I can definitely imagine that.
So this new kernels package, it completely changes the game. It downloads pre-built binaries straight from the Hugging Face hub. It just streamlines everything. You basically say which kernel you need, and the system grabs a compatible version automatically the first time you use it. No local compilation hassle.
Okay, so it's not just convenience. It's sort of democratizing access to that high-performance stuff.
Precisely. Before, you needed serious CDA know-how. Now it's almost plug and play.
And this is really interesting for GPT-OSS itself, yeah, because it's a mixture of experts model.
Exactly. MOE models lean heavily on these custom kernels. We're talking specific ones mentioned in the sources like Liger RMS norm, megablocks, MOE kernels, and even Flash Attention 3, which has support for something called attention sinks.
Attention sinks, what are those quickly?
Right. So they basically help the model keep track of important info from the very beginning of a long sequence, stopping it from sort of forgetting the early context.
Gotcha.
And you can actually opt in to use these specific kernels. You just pass use kernels. True, when you load the model. Though it's worth noting, the article mentions these specific kernels might run inference in bfloat 16 if they aren't compatible with the MXFP4 yet. We'll probably touch on that format later. But the beauty here is this dual nature. They're optimized for GPT-OSS, but things like the RMS norm kernels are general enough to be reused in lots of other models.
That's fantastic. So innovation spread quickly. Okay, shifting gears slightly, another big challenge, memory. LLMs are just notorious for being memory hogs.
Oh, they absolutely are. Gigabytes upon gigabytes, and that's where this MXFP4 quantization comes into play.
Quantization, so using fewer bits to store the numbers, right? Like going from 32-bit floats down to 16-bit.
Exactly. FP32 is 32 bits, BF16 is 16, MXFP4 takes it even further. It's a 4-bit floating point format.
Wow, 4-bit. How does it maintain accuracy with so few bits? That sounds really coarse.
It would be, but it uses a really clever trick described in the source, blockwise scaling. Instead of each number having its own exponent, it groups numbers usually into blocks of 32, and they share a single scaling factor, like a shared exponent. This lets it keep a decent dynamic range, even with just 1 bit for the mantissa and 2 for the exponent. It's ingenious, really.
And the practical impact of that, what does it mean for, say, fitting models onto GPUs?
It's huge. The article gives examples. A 20 billion parameter GPT-OSS model might fit in around 16 GB of VRAM with MXFP4. A massive 120 billion parameter one, maybe around 80 GB. That's often the difference between needing multiple high-end GPUs and potentially running on a single one. It makes these powerful models so much more accessible.
And Transformer supports this natively now.
Yes. It uses optimized Triton kernels, which, you guessed it, get distributed via that same kernels package we talked about earlier.
It all connects.
It does. You need Accelerate, kernels, and Triton version 3.4 or newer, or PyTorch 2.8 plus, and an NVIDIA GPU that supports it. Compute capability 7.5 or higher.
Okay, quite a few requirements there. What if your setup doesn't meet all those?
The nice thing is Transformers handles it gracefully. It'll just fall back to a higher precision format, probably bfloat 16, which works fine, but obviously uses about 4 times the memory, so you lose that big MXFP4 advantage.
Right.
And the blog post shows you can check a model's config easily. Just look for quant method, MXFP4. It also means you can fine-tune and save models in this format directly to the hub, which is super convenient.
Okay, so we've got efficient kernels, super compact weights. What about scaling across multiple GPUs when even MXFP4 isn't enough? Let's talk parallelism. First up, tensor parallelism, or TP.
Right, so TP is for when the model, even one layer, is just too big for one GPU's memory. What it does, as the source material illustrates quite well, is split the actual tensor, the matrices inside a layer, across different GPUs.
Ah, so you're splitting the math itself.
Exactly. Each GPU calculates its piece of the matrix multiplication in parallel, and then they communicate to gather the full result. It cuts down the memory needed per GPU significantly and keeps things fast, especially for long inputs or big batches.
And how do you use it in transformers?
It's nicely integrated. You can often just use from pre-trained and set to plain auto. It does require fast connections between the GPUs, though, because there's a fair bit of communication. So usually best within a single server.
Makes sense. Then there's expert parallelism, or EP. This sounds specific to those mixture of experts models like GPT-OSS.
It is, yeah. It's a different parallelization strategy tailored for MOEs. Instead of splitting the tensors, EP splits the experts.
Okay.
And remember, in a MOE, a token only goes to a few experts.
Right.
So you can put different experts on different GPUs. When a token needs an expert on GPU 2, its hidden state gets sent there, the expert runs, and the result comes back. The core matrix math for each expert stays on its assigned GPU. You're just shuffling the token data around.
Clever.
And what's really neat, and the blog post points this out, is that when you turn on expert parallelism in transformers using something called distributed config, it also automatically enables tensor parallelism.
Oh, interesting. So you did both.
Yeah, you get both working together. It's a kind of double whammy for scaling MOE models efficiently.
Okay, let's shift to optimizing the generation process itself. LLMs often use sliding window attention to handle long sequences without computation exploding, right?
Correct. It limits how far back the model looks at each step. Saves memory and compute.
But previously, the transformers cache for the KV cache still grew linearly with the sequence length, even if only a small window was actually being used. That sounds inefficient.
It was a bit of a missed opportunity, yeah. The cache memory would just keep growing. But the good news is, Transformers now has smarter caching. There's a dynamic sliding window layer and a config-aware dynamic cache.
Config-aware.
Meaning if the model's configuration says it uses sliding window attention, or maybe a mix like GPT-OSS does.
GPT-OSS uses a mix.
Yeah, it alternates between sliding window layers and some global attention layers. So for those sliding layers, the cache now stops growing once it hits the window size. The analysis in the source material shows for GPT-OSS, this can basically have the KV cache memory needed as sequences get really long.
Which means lower memory use, faster speeds, less latency on long prompts.
Exactly. And the best part, it's the default now. You don't need to change your code. You just get this benefit automatically.
That's a fantastic fire and forget improvement. Love those. Okay, one more speed up technique, continuous batching. I know static batching waits for the slowest generation in a batch to finish.
Leaving GPUs idle? Yeah, it's a classic problem. If you batch 10 requests and 9 finish quickly but 1 takes ages, your expensive GPU sits doing nothing for potentially a long time.
So continuous batching fixes that?
Pretty much. It's also called dynamic batching. As soon as one generation in the batch finishes, the system immediately slots in a new waiting request. It keeps the GPU constantly fed and busy, which, as the benchmarks show, significantly boosts the overall token generation throughput, how many tokens per second you can crank out.
Sounds like a no-brainer for performance. How do you use it in transformers?
There's a generative batch API for it. It's great for evaluation runs, experimentation. The sources do caution it's maybe not a full replacement for dedicated production serving systems like, say, VLLM, which have more bells and whistles for robustness.
Right, so good for testing and evaluation, maybe not for your primary production endpoint.
That's probably a fair way to put it, yeah. Production serving often needs more sophisticated scheduling, error handling, that kind of thing. But for boosting throughput in many scenarios, it's great.
Okay, one last area. Just loading these enormous models. That can take ages, right? All those tiny memory allocations PyTorch has to do on the GPU?
Oh yeah, it can be painfully slow. You're loading layer by layer, and for each one, PyTorch needs to find and reserve a little chunk of GPU memory.
Yeah.
Thousands of small allocations add up.
So what's the fix?
Well, Transformers implemented a really smart change, described as pre-stocking the pantry in the insights we looked at.
Pre-stocking the pantry. I like that analogy.
Me too. Instead of asking for memory one tiny piece at a time, it figures out roughly how much total memory it'll need on each GPU based on your device map. Then it asks the GPU for one or a few large blocks of memory up front. As the layers get loaded, they just slot neatly into that pre-reserved space. Much faster.
And is this automatic now too?
It is. If you use Device Map Auto or provide your own map, you get this faster loading by default. No code changes needed.
Fantastic.
And folks using Tensor Parallelism also benefit because related changes make loading across multiple GPUs smarter as well.
So wrapping this all up, what does this mean for you, the listener? It really shows how dynamic the Transformers library is, doesn't it?
Absolutely. It's incredibly community-driven. These powerful pieces built for a model like GPT-OSS. They don't stay siloed. They quickly become part of the shared toolkit.
Benefiting everyone, pushing the whole field forward.
Exactly. And this constant evolution moving towards a cleaner, more PyTorch native core, it's making really advanced stuff, custom kernels, fancy quantization like MXFP4, complex parallelism, way more accessible.
It feels like it's really lowering the barrier to entry for working with truly powerful AI.
It really is. Which leads to a thought, As this whole stack gets more efficient, as these cutting-edge models become easier to load, run, fine-tune, what new applications, things we maybe haven't even imagined yet, might start to emerge because the performance and accessibility hurdles are getting lower?
That's an excellent question to leave everyone with. What becomes possible next? That wraps up our deep dive for today. We really hope these insights help you on your own AI journey. Hit like and subscribe if you like the content. See you next time.